Did you know that the probability that two randomly chosen positive integers will be relatively prime, or in other words, that they'll share no common divisors other than 1, is exactly 6 over pi squared, or about 60.8%. So why is pi showing up here, and what do we mean by randomly chosen? Well, we'll see in a minute, but I should let you know that we are going to encounter two of the most beautiful results in all of mathematics, both due to Euler. Who else? The first is the Euler Product Formula. This expresses a certain infinite series over all positive integers as an infinite product over all primes. And this is such an elegant formula when you see what it's really saying and why it works. And it's actually at the center of the Riemann Hypothesis, which is one of the most important and well-known unsolved problems in all of mathematics. And the second is Euler's solution of the so-called Basel Problem. And I have a whole video on this called Can Sine Be Factored? And it's probably the video I've made that I'm most proud of. But here at the end of this video, I'll sketch out the idea of why this is true. And if you want to see the details more carefully worked out, it's in the other video. But our bigger focus here is going to be on the Euler Product Formula. So first of all, two integers, a and b, are said to be relatively prime if they share no common factors greater than 1. Or in other words, if their greatest common divisor is 1. So for example, 10 and 21 are relatively prime. Their greatest common divisor is 1. But 10 and 26 are not relatively prime. They have 2 as a common factor, a common divisor. But in general, if two positive integers are just randomly chosen, what are the chances that they'll be relatively prime? Now, I've used the phrase randomly chosen, but there is no uniform probability distribution on the set of positive integers. So the word random is a bit of a misnomer here, but let me be precise about exactly what we're claiming here. What do we mean? Well, suppose we restrict ourselves to only the numbers from 1 to 12. So we take two numbers that are between 1 and 12. What are the chances that they'll be relatively prime? Well, I've made a little table here in Excel. These numbers up and down here will represent the first number that we choose, and the numbers across the top will represent the second one. And the numbers in the table give the greatest common divisor of those two numbers. If the GCD is 1, so if they're relatively prime, then the square is yellow, and if they're not relatively prime, it's shaded blue. Well, as you can see, there's a little bit more yellow in the table than blue. In fact, there are 91 yellow squares and 53 blue squares. So 91 out of 144 possibilities are relatively prime. That's a little more than 63%. But instead of 1 to 12, what if we went 1 to some large number n, like n equals 100, or 1,000, or 1,000,000? Well, for each of those, we could calculate an exact probability that the two numbers would be relatively prime. And I've made a little table here that does that for various values of n. Notice that these percentages over here seem to be hovering a bit above 60%. And the question is, as n approaches infinity, what do these percentages approach? Now, there's no guarantee a priori that they don't just slowly creep downward towards 0 as n gets bigger. Or maybe they just keep bouncing around and don't approach anything. Maybe the limit doesn't exist. Well, our claim is this, that if we take the limit as n approaches infinity of the number of relatively prime pairs divided by the total number of pairs, where we're taking pairs of numbers from 1 to n, that this limit is 6 over pi squared. So that seems pretty crazy, but how can we show that? Well, first off, to determine if two numbers are relatively prime, we only need to consider prime factors. For example, for the numbers 18 and 30, 6 is a common factor. But that automatically means all the prime divisors of 6, so 2 and 3, will also be common factors. Now, suppose we have two positive integers, a and b. What are the chances that both of them are divisible by 2? In other words, that they're both even? Well, it's 1/2 times 1/2, which is 1/4. And the chance that they're not both divisible by 2, in other words, that at least one of them is odd, is 3/4. It's 1 minus 1/4. And the chance that both are divisible by 3, so meaning they have 3 as a common factor, well, that's unlikely, right? It's only a 1/9 chance they'll both be divisible by 3. And there's an 8/9 chance they won't have 3 as a common divisor. And we can do the same thing with 5, and with 7, and so on. Now, notice I'm not including numbers like 4 and 6, because as I said, we just need to consider primes. But I should mention that it's also true that the chances that both numbers are divisible by 6 is 1 out of 36. But we're not going to use this, and we don't want to use this, and I'll show you why in a second. Now, to say that A and B are relatively prime is equivalent to saying that they're not both divisible by 2, and they're not both divisible by 3, or really by any prime. But notice these are really independent events. If a number is divisible by 2, it has no bearing on whether it's divisible by 3. It doesn't make it any more or less likely. On the other hand, if we included numbers that were not prime, so let's say like 6, well, if a number is divisible by 6, it automatically implies it's divisible by 2 and 3. And if we know a number is divisible by 2, it's even, that makes it more likely to be divisible by 6. So since we want to have independent events so we can multiply their probabilities, that's another reason we just want to consider primes. So the chances that two numbers are going to be relatively prime is going to be 3/4 times 8/9 times 24 out of 25, and so on. It's going to be an infinite product. And I've written that out here. The chance that two positive integers will be relatively prime is this. It's the chance they don't share 2 as a common factor times the chance they don't share 3, and so on. And we do this for all the primes. Now, notice out here, these numbers are going to get closer and closer to 1, which is a good sign. It means our infinite product at least has a chance of converging. Now, we can rewrite our factors like this, because remember that where 3/4 really came from, it was 1 minus 1/4, and 8/9 was just 1 minus 1/9, and so on. Now, what we want to do is to show that this product converges to 6 over pi squared. And the way that we're going to do that is by showing that the reciprocal of this converges to pi squared over 6. So our goal is to show that this infinite product right here, and again, these are the reciprocals of the factors in our previous product that we just looked at, we want to show that this is equal to pi squared over 6. Now, how do we do that? Well, we're going to do this by showing that both sides of this are equal to this infinite series. 1 plus 1/4 plus 1/9, and so on. The denominators there are the perfect squares. And by the way, notice a key difference between these numbers in the denominators here and these numbers here. These are perfect squares, but they're only perfect squares of primes. So 2 squared, 3 squared, 5 squared. So notice this has a 16 here. There's no 16 there. This has a 36 here. There's no 36 there. But Euler showed, though, that the right-hand side here, this infinite product, is equal to this infinite series. And he also showed that this series is pi squared over 6. And to me, it's almost unfathomable that the same human being in the first half of the 18th century showed both of these things. I mean, both steps really require a tremendous amount of creative brilliance. So hats off to Euler here. Okay, so I've written this here as step 1 here, showing that these are equal, but we can rewrite this in a more compact way like this. So this series here can be written in summation notation, the sum from n equals 1 to infinity of 1 over n squared. But this product, and this symbol here is for product, just like this means sum. This product is just taken over all primes p, not over all integers. So when p is 2, we get this factor. When p is 3, we get this, and then 5, and then 7, and so on. So we want to show that these are equal. But this is just a special case, the case s equals 2, of the Euler product formula that I was telling you about earlier. So this is the Euler product formula, and when you let s be 2, we get this. So why is the Euler product formula true? Where does this come from? Well, I think it's easiest to see where the Euler product formula comes from if we first focus on the case s equals 1. It's just cleaner. Now, the one drawback of this is that for s equals 1, both sides diverge. But we're going to see that, at least formally, without worrying about convergence, both sides are equivalent when s is 1. And then it will be easier to see why the formula holds for other values of s, like s equals 2, where we do get convergence. So when s is 1, on the left side we have this. This is sometimes called the harmonic series, 1 plus a half plus a third plus a fourth, and so on. And this series is well known to diverge, to blow up to infinity. And on the right-hand side we have this product. Now you might have wondered why we did reciprocals. It seems like we just introduced fractions unnecessarily. Well, the reason is because each of the factors can now be written as a geometric series. So we're going to have an infinite product where each of the terms in the product is an infinite series. So let me explain briefly about geometric series. So if the absolute value of some number r is less than 1, meaning that r is between -1 and 1, then 1 plus r squared plus r cubed, and so on. You keep going on. You add infinitely many terms here. We get an infinite series. This sums to be 1 over 1 minus r. And this is called a geometric series. But why does this work? Well, suppose we multiply 1 minus r times 1 plus r squared plus r cubed, and we'll stop at r cubed. If you do this, if you expand this out, you're going to get a bunch of cancellation here, like r and minus r squared minus r. The only terms that won't cancel will be the first term and the last term. You end up with 1 minus r to the fourth. Now, instead of stopping at r cubed, we could really stop at any number. If we stop at r to the n, this will end up being an r to the n plus 1. So then you'll have 1 minus r times 1 plus r squared all the way up to r to the n equals 1 minus r to the n plus 1. Well, you take that equation and divide both sides by 1 minus r, and you'll have a formula for 1 plus r squared all the way up to r to the n. It'll be 1 minus r to the n plus 1 over 1 minus r. And then if you take the limit as n goes to infinity, then this formula will pop out, assuming that r is between -1 and 1. And you need that assumption in order to make the r to the n plus 1 in the numerator disappear when n approaches infinity. But this is called a geometric series. And as a quick example of this formula, suppose we let r be 1/3. What would the formula say? Well, let's say that 1 plus 1/3 plus 1/9 plus 1 over 27 and so on, and keep going up forever. It equals 1 over 1 minus 1/3, or in other words, 1 over 2/3, which is 3/2, which is 1.5. So if you start adding these terms up, and you can do this on a calculator, add more and more terms, it's going to get closer and closer to 1.5. So this formula for geometric series, we're going to use over and over again. Because notice that in this product, we have factors that are of the form 1 over 1 minus r. So this first one is 1 over 1 minus 1/2. So we can write it as 1 plus 1/2 squared, right? Plus 1/4, plus 1/8, plus 1/16, and so on. And you could do the same thing for all the factors. So here's 1 plus 1/3 plus 1/9, and so forth. And I've written it out here in one line, and I know it's going off the edge of the screen here, but it turns out that amazingly, when you multiply this out, you get this, the harmonic series. Now, why is that? Well, when you multiply this out, you need to take one term from each factor and multiply them out. So kind of like if you were to multiply a polynomial by another polynomial by another polynomial, all the terms in one factor need to get multiplied by all the terms in the next one, and so on. But this seems kind of overwhelming here because we have infinitely many factors, and each factor is composed of infinitely many terms. So how can we possibly do this? Well, in most cases, when you take a term from each factor and start multiplying it out, it's going to converge to 0. So for example, if you just did 1/2 times 1/3 times 1/5 times 1/7 and so on, that's just going to get smaller and smaller and approach 0. In fact, is there any way to not get 0? Well, yes. For example, we could do 1 times 1 times 1 times 1 and so on. Just do ones forever and we get a 1. In fact, we could get a half by doing 1/2 times 1 times 1 times 1 and so on. We can get a third by doing 1 times a third times 1 times 1 and so on. A fourth, notice 4 is not prime, but we have a 1/4 right here, times 1 times 1 times 1. We have a fifth as well. The first interesting one, though, is probably 1/6. Notice we get 1/2 times a third times 1 times 1 times 1. And in fact, that's the only way to get a sixth, right? 6 has a unique prime factorization. It's 2 times 3. The only way to get 1/6 is to do 1/2 times 1/3 times 1s forever. 1/12 would be 1 over 2 squared times 1/3, right? 1/4 times 1/3 times 1 times 1 times 1. And so the fact that every positive integer has a unique prime factorization means that you get each one of these numbers occurring once and only once. So for example, 120 can be factored as 2 times 60, and you could keep breaking it apart, and you end up getting 2 cubed times 3 times 5. That's the prime factorization of 120. So if we go back here, how can we get 1 over 120? Well, we get 1 over 2 cubed times 1/3 times 1/5, and then times 1 times 1 times 1 forever. So it's really the fundamental theorem of arithmetic that we're using. Every integer greater than 1 has a unique prime factorization up to the order of the factors. Now, again, this is a harmonic series that actually diverges, and this will diverge. But we're actually interested in the case 1 plus 1/4 plus 1/9 plus 1/16, and so on. And in fact, what you can show is that for s equals 2, so we're using 2 here, we can write it out the exact same way. It looks slightly messier because you have all these squareds on all the terms. But everything ends up being the same as before. So we have 1 over 1 minus a fourth, and we expand that into the series 1 plus a fourth squared plus a fourth cubed, and so on. And we do that with all these. So notice the main difference between this and the previous one is that we have these squareds in here. But again, you end up getting this series here. And notice we have squareds on them. So for example, where is the 1 over 6 squared coming from? Well, it's 1 over 2 squared times 1 over 3 squared. So again, you're factoring 6 uniquely as 2 times 3. So it's the same reasoning, the fundamental theorem of arithmetic, that says that this product is equal to this series. But now in this case, the case s equals 2 here that we're looking at, both sides converge. So that's where this incredible Euler product formula comes from that says this product is equal to this series. You take each factor here and expand it into a geometric series. You recognize the prime powers that occur in the denominators once and only once. And then by multiplying everything out and using the fact that every positive integer has a unique prime factorization, you get this series. So it's really quite amazing where this comes from. Okay, now we've completed this incredible step of showing that the product here is equal to this sum. Now we want to show that this series converges to pi squared over 6. And trying to find the exact number that this series converges to is known as the Basel problem. And this was in the early part of the 18th century. Mathematicians had calculated a bunch of decimal places, but nobody knew exactly what this number is until Euler came along and showed it converges to pi squared over 6. And it's really one of the great stories in math history, and I have a whole video on it, and you should watch it. But here I'll give you a rough sketch of how he did it. And what he did was to factor the sine function. So this is the so-called power series expansion for sine of x, which you'll learn about in a second or third semester of calculus. And this is just a beautiful formula in its own right. But this was known to Euler, and he kind of thought of this as saying that sine of x is in some ways like a polynomial. And if we can factor polynomials based on their zeros, maybe we can factor the sine function. And the zeros of sine occur at the multiples of pi. And so Euler discovered that you can factor sine like this. Now, this might not be the factorization that we would think of because we're not Euler. We might think to do x minus pi times x plus pi times x minus 2 pi and so on. But the problem is that product wouldn't converge. But this way of doing it does converge. And the reasoning behind why this converges and the other way doesn't, well, it's in my other video, but the basic idea is that for any particular x value, these factors are going to approach 1 as we go further and further out here. And that wouldn't happen with the other way of trying to factor it. And then what we can do is to combine factors. So combine these two factors to get this, combine these two factors to get this, and so on. And then you write it in product notation like this. And notice each factor has this form. We have an n squared here because of these perfect squares right here. And we also have a pi squared in each of the terms. But this is how sine factors. And again, the details are worked out more clearly in my other video, but sine of x is equal to this infinite product. And then we're going to take both sides and divide by x. So we're going to get sine of x over x equals this product. And that's what I've written right here. Next, what Euler did was to take both sides of this equation and expand them into power series expansions. So for the left-hand side, we can write sine of x over x as just 1 over x times sine of x, and this is the power series for sine of x. Distribute the 1 over x, and we get this. And notice that the coefficient of x squared here is negative 1 over 3 factorial. It's negative 1/6. Then we take the right-hand side and expand that into a power series. So we go down here and write it out. And we have this infinite product that we're going to have to expand, just like we did earlier. This time, though, instead of having infinitely many terms within each factor, we only have 2 terms. But we still do have an infinite product. We have infinitely many factors. And when we do this, we can get a 1 by doing 1 times 1 times 1. There's no way we can just get a linear term in x terms. We have 0x. Now our x squareds come from doing something like minus x squared over 4 pi squared times 1 times 1 times 1. We can also get this by doing this times 1 times 1 times 1 and so on. And we get this for our x squared terms. And we'll have higher degree terms as well. But for the x squared term, notice we can factor out the x squared and what we're left with is this. So our coefficient of x squared here is this. Up here, it was minus 1/6. So comparing our coefficients of x squared, we get that this is equal to negative 1/6. Well, and then if you just multiply both sides by negative pi squared, you get this. And that's the solution of the Basel problem. And so this ties it all together for us. And so crazily enough, the reason that pi gets involved in the probability of two randomly chosen integers being relatively prime is because the zeros of the sine function occur at the multiples of pi. And it's insane to me to think that the sine function has anything to do with the chances of two numbers being relatively prime. But there it is. Well, thank you for watching. The other video on can sine be factored is on the end screen here. And so if you want to see that, just click on that right there.